All right, so hi everyone, welcome back. Very good evening to you all. Myself, Ayush Tripathi, and welcome you all to this post-analysis discussion of the last Job-A-Thon, which is Job-A-Thon 44. So before starting the discussion, I want you guys to just rate the entire contest on a scale of 10 so that we can improve the upcoming problem set. And also just tell me how many problems you were able to solve. And also write a quick +1 if I am perfectly audible to you as well as I am visible. Cool. So everything seems good to me. Okay, just allow me 1 minute. All right. So starting with the first problem, geek and permutation. So in this problem, geeks loves permutation and has a special fondness for the number 4, for the integer 4. And given a permutation ARR of integers from 1 to n, and we define the cost of a permutation by the sum of absolute value between the indexes and the element value. And your task is to find the total number of permutation of size n that cost is exactly equals to 4. And here we have a formal definition of a permutation. So starting with this first example, n is equals to 3. And one very important thing, the value of n can be up to 10 power 9. So you cannot iterate over all the possible permutation. So that's why we need to come up with some formula. So let's see how we can solve this problem. So for n is equals to 3, this will be these are the three permutation which has a cost 4. For n is equals to 4, these are the 7 permutation which has a cost 4. Now coming to the solution. So the cost of the permutation is basically the sum of all the values from index I to index n and the absolute difference between the index and the element value. So this will be your total cost. ARR of I, this is the index value, and then I is the index number. So sum of all the absolute differences. And you have been given integer n, and you need to count the number of permutation. which has cost 4. So the very first thing, let's say we have a permutation n, and from 1 to n, let's say n is equals to 5. And let's consider a very simple permutation: 1, 2, 3, 4, and 5. All the numbers in an increasing order. So this is my index 1, then index 2, then index 3, index 4, and index 5. So here what will be your cost? So your cost will be 0, because at all the indexes we have the same number. So in this case the cost will be 0. And what we wanted to have, we want to have the cost is equals to 4. So how many such permutations are possible? So the very first thing, what if we swap two adjacent number? So from this permutation, let's swap two adjacent number. There's a number 2 and 3. So what will be the cost in that case? So 1, then a 3, 2, and all the integers will remain as it is. So in that case, the cost will be equals to 2. So what I'm trying to say, whenever you swap two adjacent number, then your cost will increase by 2, right? And now let's swap these two numbers. So if I swap these two adjacent number, then what will be my cost? Then my cost will again increase by 2. So 2 plus 2, it is equals to 4, right? This is same as the desired cost. So what I'm trying to say, if you swap two adjacent number, then your cost will increase by 2. So how many numbers we need to swap? So let's consider this as a block. So consider this as a block 1, and let's consider this as a block 2. So I need to find the two blocks such that the blocks are not overlapping, and then I will swap the numbers which is inside the block. So the block offers two elements, right? So let's formulate this thing. So this will be my case 1. To achieve the cost is equals to 4. So I can say case 1. So in case 1, I need to find the number of ways to select two non-overlapping block of adjacent element. So let's just first find how many blocks are possible. So let's say n is equals to 5, n is equals to 5, then how many blocks are possible? Or I can say how many pair of adjacent numbers are possible. So the first pair, which is 1, 2, this is one pair. Then second pair could be 2, 3, then 3, 4, then 4, 5. This is my fourth pair, and only these four pairs are possible. So how many pairs are there? There will be exactly n minus 1 number of blocks, or I can say n minus 1 number of pairs. So out of n minus 1 number of pairs, or I can say out of n minus 1 number of blocks, you need to find the number of ways to select two blocks. So how many number of ways are there? So it is simply equals to n minus 1 C2. So number of ways, it is equals to n minus 1 C2. But in this number we have also counted the invalid configuration. There are some configuration which are invalid. For example, if you select this block and if you select this block, then these two blocks are overlapping. So such type of configurations are invalid. And out of all the all the possible configuration. If I subtract the number of configuration which are invalid, then eventually I will get the number of ways to select two non-overlapping block of adjacent element. So let's subtract the invalid configuration. So when I say invalid configuration, it simply means overlapping block. Overlapping block. So how many overlapping blocks are possible? So 1, 2, then 2, 3, 3, 4, then 4, 5. And how many overlapping blocks are possible? So either I can select these two, then the blocks will be overlapping, or I can select these two, then the blocks will be overlapping. So either I can select these two, blocks are overlapping, or if I select these two, then also blocks are overlapping. If I select these two, then also the blocks are overlapping. So basically there will be only 3 configurations which are invalid. So from this number, from this total number of ways, I need to subtract 3. So basically the count will be equals to n minus 2. So this count is equals to n minus 2. So there will be n minus 2 configuration which are invalid. So my total answer for the case 1, it is equals to n minus 1 C2, that is total number of ways, and out of total number of ways I will select the invalid configuration, which is n minus 2, right? And let's further solve this expression. N minus 1 C2, it is equals to n minus 1 multiplied by n minus 2 and divided by 2, and then I need to subtract n minus 2. So let's take this n minus 2 common. So n minus 2, then n minus 1 divided by 2 and minus 1. Now if you further solve this equation, then you will get it is n minus 2 multiplied by n minus 3 and divided by 2. So this will be my answer for the case 1. Now I need to check, is there any other case or not? Now coming to the case 3, case 2. So case 2, when I select the 3 adjacent elements. So let's say you decided to select a 3 adjacent element. So element with the index I. So the next element should be at index I plus 1, from the index I plus 1, then I plus 2. So I'm going to generalize the formula. So these are the indexes of a 3 adjacent element, right? And let's now find the all possible configuration. So there will be 6 permutation possible. That is a 3 factorial, which is equals to 6. So 6 permutation are possible in total. But out of 6 permutation, there are 3 permutations only, which will give you the cost is equals to 4. So do not get confused. Before this element, this index I, all the values are equals to 4. all the elements will be at their original position, and after this index I plus 2, all the elements will be at their initial position. That is, at index j, we would have the element j. Cool. Now let's swap these two values. That is a value at index I and the value at index I plus 2 with the value at index I plus 2. So that is I plus 2, and then at I plus 1 we keep the value as it is, and at index I plus 2 we would have I. So in this case, what will be the cost? So the cost will be equals to 2 plus a 0 and plus 2, which is equals to 4. So this is one possible way how you can achieve the cost is equals to 4. Now let's see if we have any other configuration or not. So now let's swap these two values. And we keep this value at here. Okay, so let me write it over here only. So at this position, at index I will keep the value I plus 1. At index I plus 1, I will keep the value I plus 2, and at index I plus 2, I will keep the value I. So in this case, what will be the cost? So the cost will be, in occurred cost will be 1 plus 1 and plus 2, which is equals to 4. Again, same as the desired cost. Now let's find one more configuration. So let's keep the value at index I plus 2, and let's keep here value I, and let's keep the value I plus 1 at index I plus 2. So in this case, what will be the cost? So the in-occurred cost will be 2 plus 1 and plus 1. It is equals to 4. So out of 6 permutation, so 3 factorial, it is equals to 6. Out of a 6 permutation, 3 permutation will give you the cost 4. So yes, these are the 3 valid permutation, right? So what I'm trying to say, now let's say we have an object, or I can say an element. Hi, good evening, Neeraj. So we have an element, and out of the n element, tell me the number of ways to select 3 adjacent elements. So how many number of ways will be there? So basically you have an element 1, 2, 3, 4, 5, 6, and let's say 7. So how many possible ways are there? So one possible way is to select these 3 adjacent element, then select these 3 adjacent element, select these 3 adjacent element, or you can select these 3 adjacent element, then we can select these 3 adjacent element. So basically we just only have to keep the 2 elements separate, the last 2 element, and then we can select all the possible 3 adjacent element. So how many number of ways are there? So number of ways to select 3 adjacent element out of n element. It is equals to n minus 2. Now if you select more than 3 adjacent element, then your cost will be greater than 4. So all the configuration will be invalid. So my final answer will be equals to case 1, the result of case 1 plus the result of case 2. So case 1 we have n minus 2 multiplied by n minus 3 divided by 2 and plus n minus 2. This will be your total answer. Now coming to the implementation. So this is my case 2. This is my case 2 and this is my case 1. And make sure to use the appropriate data type to avoid the overflow condition. So I hope it is clear to everyone. Now the time complexity is constant. We have a constant expression, constant time expression. Now coming to the next problem of the contest, maximize candies. Okay, so this is the third problem. This was the third problem, and this one is the second problem. So you have been given a tree of n node, which is rooted at vertex 0, and each node is numbered from 0 to n minus 1. And all the edges are given by this 2D array edges. So edges of I, it is equals to u of I comma v of I. So there is an edge from u of I to v of I, and the edges are bidirectional, basically u to v, or I can say v to u. And your task is to find the number of a path starting from each subtree which is rooted at vertex I. So basically you need to consider the subtree starting from each vertex I and count the number of paths such that the count of odd node in the path, it is equals to the count of even node in the path. And you have to return an array of size n where the ith element is the number of such path starting from the subtree which is rooted at vertex I. Then the maximum depth of the tree is at most 200. So this is another constraint. Now here the examples are very small, so I can explain you with some better example. So let's consider the root node 0, and let's say we have an edge from 0 to 1. Then let's say we have an edge from 0 to 4, or I can say 0 to 3. Okay, let's keep this as 4. Then let's say we have an edge from 4 to 3, and let's say then from a 3 to 2, and let's say from a 4 to 6, and 6 to maybe 5, and here we have, let's say, 1 to 7. So let's consider we have this tree. So how many paths which are valid? So let's consider the subtree which is rooted at vertex 0. So how many valid paths we have? So the path from 0 to 1, it is valid, right? It has one odd node and one even node. Then path from what I can say, is there any other valid path? So basically this path is valid. Then the path from 0 to 7, it is invalid because it has two odd node. Then path from 0 to 4, then path from 0 to 4, then from 4 to 3, it is still not valid. Then from 3 to 2, and now it is valid. We have a two odd node and two even node. Okay, sorry, my bad. It is still invalid. We have a three even node and one odd node, so it is still invalid. Now let's consider this path invalid. We have all the even node. Let's consider this path and it's still invalid. So basically there is only one valid path which is start with the root vertex 0. Now let's consider the subtree, which is rooted at vertex 4. So what are the valid path we have? So the only valid path is from 4 to 3. So this is the only valid path, 4 to 3. Now let's consider the vertex. Let's consider the subtree which is rooted at vertex 6. So the only valid path is from 6 to 5. This is the only valid path from a 6 to 5, right? So this is the definition of a valid path. If the number of odd node and the number of even node in the path are equal, then only I can say the path is valid. Now let's represent the odd node with the value 1. So let's represent the odd number node with the value positive 1, and let's represent the even number of even node with the value -1. So if any path is valid, so the path is valid if and only if the difference between the odd number of node and the even number of node is equal to 0. So the difference, which is odd number of node minus even number of node. So I can say count odd and count even. So the absolute difference between count odd minus count even, if it is equals to 0, then only I can say the path is valid. So this is one representation which I have used in my implementation, and we're also going to explain with the same assumption, that is representing odd with the positive one and even with the negative one. So if the absolute difference is 0, then only I can say the path is valid. Cool. Then from every child, I need to return some information. So what I'm trying to say. So let's consider the new subtree. So vertex 0, then let's say vertex 1, vertex 2, vertex 3, or I can say then vertex 4, and let's say vertex 5, vertex 6, and let's say vertex 7. So for every node, I required some information from the child node. So the idea here is to apply the DFS algorithm and modify the DFS algorithm. So use modified DFS algorithm. Now how we modify this thing? So from every child, we need some information. So extract some information from the child node. And this is basically a very trivial solution of a DFS algorithm. So for example, let's say we are at a node 0. Let's say the current node is 0. Let's say this is your current node. So what are the information we required? So the very first thing, I need to know what are the possible paths which start from this node. So basically, I will make a call to all its neighbor. I will make a call for this node 1. I will make a call for this node 2. And then I will ask one thing. Tell me the number of path which is present and is starting from you, and what is the value. That is how many odd node are there and how many even node are there. So for this thing, I'm going to return a map. So some information which is in a form of map. So return map. And what this map will store? So this map is nothing but the key value pair. Now key will be number of the key will be difference. This key is nothing but it will be difference. And what is the value of a difference? So the value of a difference, it is equals to the absolute value of a odd node. So basically count odd minus count even. This is the value of a difference. So my key will be difference and this value will be number of path. So for example, starting with this root node 0. So starting with this root node 0, then I will make a call to visit all its a child. Let's say we decided to make a call to visit 1. Then I will make a call to visit 3. Then I will make a call to visit 4. Right? Then I will make a call to visit 4. Now this 4 do not have any other child. Right? So here we are going to return some information to the parent function. So what information I will return? So the initial difference it is equals to 0, right? And what if I add one even node? So if I add one even node, do not get confused. Odd is going to be represented by +1 and even is going to be represented by -1. You can also do the opposite, that is odd with the -1 and even with the +1. So the initial difference is 0. Now since I got one even node, so I will simply update the entry. I will simply insert the entry in my map. So that is map of -1. Now the difference is -1. So 0 -1, which is equals to -1. It is equals to 1. That is one path emerges which has one even number of node. Now I will return this information to the parent function. So the parent function is 3. The parent function is 3. Now here what is the difference? So the initial difference again 0. So now I'm going to check what is the value of a current node. So the value of a current node, it is equals to 3, and this 3 is the odd number. This 3 is odd number which is represented by +1, right? So now I'm going to ask the query from the child node, that is how many paths are there for which the difference is -1, because +1 -1 it is equals to 0. So basically there are only one node. So I will increment my answer, that is answer of 3. The answer of 3. So this answer is an array which we are going to return. So answer of 3 which was initially has value 0. Now I will increment the value with 1, right? And what information I need to return? So what information I need to return? So there are two possible paths. The path might end at vertex 3 or it might extend up to the vertex 4, right? So what if the path end at vertex 3? So in that case, what will be the difference? So if the path end at vertex 3, then in that case, the difference will be +1, right? Because this 3 is a positive, this 3 is a odd value, so we add positive in the difference. So that's why map of 1 it is equals to 1. And what if this path end at vertex 4? So in that case, map of 0 it is equals to 1, right? and at the same time I need to remove this entry because it is no more exist. All the path must have to include the vertex 3. So either the path has to be stop at vertex 3, or it has to be extended till vertex 4. So that's why I need to delete the previous entry. Now this will be my new map. Coming to the parent function, which is 1, and now it's time to calculate the answer for the parent function. So the current value it is 1, right, which is odd, and odd is represented by a positive 1. So now I'm going to ask one query. Tell me how many paths are there. Tell me how many paths are there which has the difference -1. So -1, then a +1, so that it will be equal to 0. Valid path. But there is no path which has the value -1. So that's why it is not possible to have any valid path which emerges from vertex 1. So the answer for vertex 1, it is remain equal to 0. Cool. Then what I will return to the parent function? I will return to the parent function the updated map. So what is the updated map? So the very first thing, it might be possible when the path end at vertex 1. So in that case, map of 1. So this 1 is basically odd node, and odd is represented by a +1. So map of 1, it is equals to 1. Then it might be possible when your path end at vertex 3. So we have two odd node. So the difference is 2. So map of 2, it is equals to 1. Then it might be possible when the path end at vertex 4. So in that case, what will be the difference? So +1 and -1, because this 4 is a even number. So your difference will be +1 +1 and -1, which is equals to 1. So just simply increment the value by 1. Now it is equals to 2. So that is we have a two path in which the difference is odd. So I hope it is clear to everyone. And then we need to delete this map. This is my new map which I'm going to return to the parent function. Now coming to the parent function. So the parent function, which is node 0. So here the value of a node is 0, which is even. So it simply means it creates a difference of 1. It creates a difference of 1 because even is represented by, sorry, it will create a difference of a -1 because even is represented by negative number, right? So now I am interested to know, how many paths are there which end with the difference of a positive 1, so that I can simply add this -1, the difference will be converted to 0. So how many possible paths are there? It is 2. There are two possible paths. And what are those two possible paths? The path from 0 to 1, this is one possible path, and the path from 0 to 4. Both the paths are valid, right? So that's why we increment the answer of 0. Previously it was 0, and now incremented by 2. So I hope this is clear to everyone. Now coming to the next call. So we make this call, and coming to this node 2. But basically now you can try run by yourself, but this is the idea. Every time we return the map to the parent function, and what this map will store the key, the difference as the key, and the value as the number of path. And what are the possible value of key? That is how many unique pair we can have. So the possible value of a difference, it is in the range from -n minus 1. So it is in the range from -n-1, or basically not minus, but what I can say, yes, the minimum possible difference, it is -n, or even it is not possible -n/2. There will be at most n by 2, n by 2. There will be at most n by 2 minus n by 2 value of a difference is possible, minimum. And the positive value is n by 2, right? So yeah, these are the possible value of difference. So I can say the maximum size of the map. So in this way, we can solve the problem in n log of n base 2 time. Now coming to the implementation. So this is the method that you need to complete. Then here I have taken the size of this edges vector and plus 1. Basically, the number of edges will be n minus 1. So plus 1 to get the value of n. Now clear this adjacency vector. Clear this adjacency vector, and then simply add all the edges. Then declare the answer of size n. Then call this function. This is basically a DFS function. Iterate over all the neighbors, and if the neighbor is present, if the neighbor is parent, then skip the neighbor, right? Otherwise, you make the call to the child node, and it will return me the map. Then I'm going to store all the entries in the child sum map, right? And then child sum of 0, it is equals to 0. This is for the case when I have to end the upcoming part at the current node. So it might be possible, let's say you are at this node 1. So what information you will return to the parent function? So I need to return. So it might be possible that the path from which we are coming from is end at this vertex 1, right? So that's why initializing the difference with 0, so that if I add the value of a current node, so the value of a current node, it is 1. So basically it is odd, and for the odd we add the value 1. So that's why I'm going to update the entry, that is map of 1. Previously it was 0 and now increment it by 1. Cool. Then this is my current map, which I'm going to return to the parent function. If the current node is odd, then increment this value by this vector, and this is from the child sum path. Otherwise, if the value is a minus 1, then decrement the, if the value is even, then it is represented by minus 1. And finally my answer will be the number of path for which the difference is 0, and I'm going to return this information to the parent function. So that's the complete solution of this second problem. The time complexity is not n square. Do not get confused with this thing. It is much lesser than n square, somewhere around n log of n base 2. Now coming to the last problem of the contest. Maximize candies. So in this problem, you are given an array candies of integer candies, where candies of I is the amount of candies of type I, and you have at most k bags. You have to distribute candies such that each bag which you want to fill has the equal number of candies or can be empty. So basically the number of candies in each bag must be same or either 0. And the total sum of candies in all the bags should be maximized. Each bag can at most hold at most one type of candy. This is another very important constraint. Each bag can hold at most one type of candy. That is, you cannot mix the candies from two different bags. Find the minimum number of candies in each bag such that the total sum of the candies in all the bags is maximized. So basically we need to minimize the number of candies in each bag, and we have to maximize the sum of all the candies. And again, some bag can be empty also. So coming to this example, let me take an arbitrary example. For example, let's say n is equals to 4, and let's say k is equals to 12, or I can say k is equals to, let's say, 3, or what I can say, let's say it is equals to 6. So basically at most we can have a 6 number of bag. So candies array of size 4. So the number of candies of type 1, let's say it is 7. The number of candies of type 2, let's say it is 8. The number of candies of type 3, let's say it is 2. And the number of candies of type, let's say 4, let's say it is a 3. So now we need to distribute the candies very efficiently, such that the sum of candies is maximized. So what are the possible distribution? So what can I do? I can distribute the candies. So we can have at most k bag. So bag 1, then bag 2, then bag 3, 4, 5, and 6. So initially all the bag has a 0 candies. Now what I can do, I can add 6 candy here, then I can add 6 candy here, and let's also increase these value. Let's say it is a 10 and it is 9, and I can add 6 candy here, and let's also add a 6 candy over here. So what I'm trying to say, this is one possible configuration to maximize the number of candies. But we can have some better option. So instead of having this, let's distribute the candies in this way. That is a 5 candy of type 1, then 5 candy of type 2, then 5 candy of a type 3, again 5 candy of type 3, and then 5 candy of type 4, and keep the last bag empty. Keep the last bag empty. So in this way, we can maximize the number of candies, and also the candy in each bag is minimum. So the minimum. So in this case, my answer will be equals to 5. Now, how we can solve this problem? So coming to the solution. So the very first observation, let's find the maximum value of this candy array. It is clearly mentioned in the problem statement that we cannot mix the candy. Each bag can hold at most one type of candy. So what is the maximum number of candy in any bag we can have? So let's call this as observation. So what is the maximum number of candies in any bag we can have? It is always less than or equals to the maximum element of this array. You cannot have a bag which has more than 10 candy. At most, you can place all the 10 candy of the same type in a single bag, right? So this max is nothing but the maximum element of the array. So this max is nothing, mx is nothing but the maximum element of this candies array. Now one thing I know, the maximum number of candies in any bag that we can have, it is less than or equals to this mx. So let's iterate over all the integers from 1 to mx. So for c is equals to 1, and up to mx. So at this point of time, I am going to explain you the brute force solution, that how I came to the come to this idea to solve this problem, and will later on optimize the solution. So basically now I'm going to consider all the integer from 1 to just mx, that is all the integer from 1 to 10. And now I decided to place exactly c number of candies in each bag, or we keep the bag empty. So the second step, place exactly c number of candies in each bag, and the possible range for this c is from 1 to mx. Cool. Now we iterate over all the indexes, or I can say all the possible candies, possible type of candy from 0 to n minus 1. So how many possible bag we can have? How many possible bags we can have? So initializing the number of bags that we can make with 0, and let's say the value of c, it is equal to 3. So from the candy of a type 1, how many bag we can create? So from here, the number of bags that I can create, it is 2. From here again I can create only 2 bag. I can create 3 bag from here, and I can create 3 bag from here, right? So if the number of candies of type if the number of candies of type I, let's call this as a v. If the number of candies are v, then the number of bags will be, I can simply write in this way, that is number of bags will be candies of I divided by k, divided by c, not k, and take the floor value. So for example, this is 7 by 3, which is equals to 2. Then 8 by 3, it is equals to 2. 10 by 3, it is equals to 3. Right? So the contribution of a ith type of candy. So bags plus equals to I divided by C. And after this, after this, you need to check how many bags at most we can have. How many bags at most we can have? So the at most number of bags that we can have, it is 6. So the sum of candies will be minimum of the number of bags that we can form, maximum number of bags that we can form, and the number of bags which we can have. It is given in the problem statement. There's an integer k, and multiplied by c, the number of bag into the number of candies in each bag. So in this way, you can check whether the answer is updatable or not. And if the answer is updatable, you got the better result. Then update the answer with the value of c. So in this way, you can solve the problem. But there is a problem. The time complexity of this solution, it is mx into the size of this array, which is n. Now let's analyze the constraint. The value of mx can be up to 10 power 5, the maximum value of array, and the size of this array can also be up to 10 power 5. So 10 power 5 multiplied by 10 power 5, which is equals to 10 power 10, and this solution will definitely give you TLE. So we have to do something better. Now, how we can optimize this process? How we can optimize this process? So we need to do some pre-computation. So previously what I did, for every possible value of c in the range from 1 to mx, we iterate over all the indexes. But now I'm going to optimize this process. Instead of iterating over all the possible indexes of the array, we iterate over the multiple of c. We iterate over the multiple of c. Now coming to the optimized solution. So definitely we iterate over all the integers from 1 to mx, no doubt. And the value of mx, it is equals to the maximum element of the candies array. Cool. And now I'm going to iterate over the multiple of c. So what are the multiple of c? So the first multiple of c, it is c itself. So the first multiple of c is c itself. Then second multiple 2c, third multiple 3c, then 4c, and so on up to lambda c. And this is the highest multiple of c, which is less than or equals to mx. So basically this is the highest multiple less than or equals to the maximum value, which is mx. Or more formally I can say lambda plus 1 multiplied by c, it is greater than mx. So this lambda c is the highest multiple of mx. Cool. Now next, what we have to do next? For every multiple of c, let's consider the current multiple of c. It is p multiplied by c. So let's consider the current multiple of c. It is p into c. Now we are interested to know how many bags are there, or I can say how many type of candy are there which are having these many candy initially or greater than this. So for example, let's consider the current multiple. So let me write a for loop here. So for p is equals to 1, or I can say p is equals to c. P is equals to c, while p is less than mx. This p is nothing but the multiple of c. So p is less than or equals to mx, and every time we update the p by adding the value of c. That is, take a jump to the next multiple. So let's consider the current value of p. It is equals to m into c. Definitely, it would be some multiple of c, because every time we iterate over the multiple of c. So from c, then 3c, then 4c, 2c, and so on. Right? So this is called as let's say I can write it in this way. Let's say it is a what I can say alpha into c. Let's call this as alpha into c. Alpha into c is the multiple of c. Now, for example, let's say we have some bag candies of I, and it is having a value. It is having a value which is in the range from alpha into c. This is the minimum value, basically in the range from alpha into c, and up to alpha plus 1 into c, and let's keep this value as exclusive, or I can say simply subtract 1 from here. Now if you are having these many candy of type I, then how many bag you can form? The number of bags that you can form, it is nothing but exactly equals to the alpha. So the alpha number of bags you can form from this candy of type I. So it might sound a bit confusing to you. So let me explain with an example. So let's say the value of c it is equals to, let's say it is equals to 5, and let's consider the current multiple, it is equals to 30. So the value of p, it is equals to 6 multiplied by 5. So the value of alpha, it is equals to 6. And let's say you have a candies of I, candies of I, and initially the number of candy of type I, let's say it is in the range from, let's say it is in the range from 30 to 34. If it is in the range from 30 to 34, let's say, let's pick a random value in this range, let's say 32. So how many bag you can form? So the number of bag that you can form, the number of bag that you can form, it is exactly equals to alpha. It is exactly equals to 6. So 6 number of bag you can form. You cannot form the seventh bag. You cannot form the seventh bag, because after having the sixth bag, and each bag with the 5 candy, then you cannot form the seventh bag. So we can only have the alpha number of candy. Now the next thing, we need to have this information. We need to have this information for a particular multiple of p, for a particular multiple of p, multiple of c. I need to know how many candies are there which are in this range. So for this, we need to do some pre-computation. So for the pre-computation, what I'm going to do, I'm going to use a suffix array. I'm going to use a suffix array. So suffix array of size mx plus 1. Suffix array of size mx plus 1. And I will initialize all the value with 0. So we'll simply initialize all the value with 0. And then iterate over all the candy and update the value corresponding to it. So what I'm trying to say, let me explain you with the same example. This one. So here the maximum value, it is equals to 10. So I will create a suffix array of size 10 plus 1, which is equals to suffix array of size 11. And initially I'm going to fill all the value with 0. So let me create an array of a size 11. Now we are going to update all the value. So we have a one candy. So we have one type of candy which initially has value 7. So here I will fill 1, and then 8. So here also I will fill this value with 1. So basically I iterate over all the candy. For all the candy, let's say, let's call this value as E, and that's a candy array. So in our candies array, now simply increment the value of index E. So increment all the values were initially 0. So then suffix of 7 incremented by 1, then suffix of 8 again incremented by 1, then suffix of 9 incremented by 1, suffix of 10 incremented by 1, right? And then simply update the suffix array. That is, iterate over all the integers from mx minus 1 to 0, and update all the value. So suffix of I plus equals to suffix of I plus 1. So basically what the suffix of I will store, so suffix of I will simply store the number of types of candy number of types of candies which has initial count greater than or equals to I. So this is what I will store in a suffix of I. So then simply update all the value, that is suffix of I plus equals to suffix of I plus 1. So update this value with 2, update this value with 3, update this value with 4. Let me change the color here. And update the rest of the value with 4 because all the values are 0. All the values are 0. Now after getting this information, I can easily find the number of candies. Or I can say the number of type of candy which are having the initial count greater than this value, and then I will just simply add the number of bags, the total number of bags. I will just simply add this value alpha in the total number of bags. Now coming to the time complexity, the time complexity will be order of mx multiplied by log of mx base 2. Now some of you might ask that we have this for loop which iterate over the multiple of c. But yes, this for loop will take logarithmic time only. So the sum of this for loop will only take the logarithmic time. It is nothing but the harmonic sum of multiple. And the harmonic sum of a multiple has the upper bound logarithmic. So that's the complete solution. Now coming to the implementation of the problem. So finding the maximum value, then updating the suffix array, and then take the suffix sum, suffix of I plus equals to suffix of I plus 1, initializing the answer with some bigger value, and count is equals to 0. So this count is basically store the maximum sum of candy. Iterate over all the integer from 1 to mx. Then this total is the total number of bag that we can have. Then iterate over all the multiple of I. This I is nothing but the c. Iterate over all the multiple of I, and this total will simply store the number of bags which we have, number of bag which has the initial count greater than or equals to this current multiple. Cool. Now how many bags we can have? We can form. So the total minimum of total comma k and multiplied by I. This is basically c. And if the total sum is greater than whatever the sum we have stored, so it simply means now we got the better result. So update the total sum and also update the answer. And finally I will return the answer. The time complexity is 10 power 5 multiplied by log of 10 power 5 base 2. So that's the complete solution. So if there was something which is not clear to you, then you may have to revisit the lecture, especially for the last problem. It was a bit hard. So just go and again rewatch the recording of this session and take a multiple pause. That definitely it would be clear to you. The only crux of the problem, we need to iterate over the multiple of c, and for every multiple of c I need to have some pre-computation, which is nothing but the suffix array. So yeah, that's all for the today's contest, and I hope you have learned something new. Thank you everyone for watching this video or attending this live stream, and have a good day. Good night.